Welcome to lecture 41 for numerical methods of differential equations. So today we're going to be looking at solving systems of ordinary differential equations numerically. So in unit 4, we learned how to solve analytically or exactly systems of ODEs. But some systems, again, we are not going to be able to solve those analytically. So sometimes we have to use numerical methods on systems as well. So just by way of revision, recall from Unit 4 that an nth order ODE can be written as a system of first order ODEs. So if we're given this single ODE, the scalar ODE, y double prime minus y equals 0, we can convert that into a system of first order linear ODEs, okay? So this is all revision. So for the second order ODE above, we're going to introduce this new variable x1. And the definition of x1 is going to be that x1 is equal to y prime. Okay, so the derivative of y. Now if I differentiate x1, then I get x1 prime is equal to y prime, or let's say x1 prime is equal to the derivative of y prime, which of course is just the second derivative of y. Okay, so here we have a differential equation for the variable y, this first one here, and here we have a differential equation for the variable x1. Okay, but y double prime here, the right hand side of x1 prime equals y double prime. If I look at the original ODE, I can rearrange this to write y double prime equals y. Okay, so I'm going to replace y double prime in this ODE here with y double prime equals y. Okay, so I get this ODE effectively here, x1 prime equals y. So now I have two first order ODEs, y prime equals x1 and x1 prime equals y. Okay, fantastic. So here's my system of ODEs. So I'm going to let the vector x equal x1 and y, this vector of x1, y. Again, I've written x1 first here. It doesn't actually matter if you write y or x1 first, as long as you're consistent in the next matrix, so in the matrix A. So for the x1 variable, x1 prime equals 0 times x1 plus 1 times y1. So that's why we have the 0, 1 in the first row here. Y, for the y differential equation, y prime equals 1 times x1 plus 0 times y. So that's why we have 1, 0 in this denominator. If you did happen to write the ODE in the other way, so you wrote x is equal to y, x1, then the rows of A would be inverted. They'd be switched, in fact. Okay, so the second order ODE above can be written then, using this method, as a system of first order ODEs in matrix form. Okay, and of course we also looked at examples here where we looked at higher order examples where we had to introduce two new variables. So just by way of reminder, we introduced the variable x1, which is equal to y prime. We introduced x2, which was equal to x1 prime. And then we took the derivative of that, and we ended up with three first order ODEs, okay? In fact, first order linear ODEs. Okay, and we could write that as in this matrix form. Okay, and of course we looked at the eigenvalues of this matrix A to try and understand something about the solution of this system. But often we can't find the exact solution to these systems. So what I'm going to do is I'm going to introduce a way to solve these systems of first order linear ODEs numerically. In fact, they don't have to be linear even. They just have to be ODEs. A system of ODEs. Okay, so we have this system here. So we've got in this case, n first order differential equations. I also have n initial conditions here. So x1, x2, all the way through to xn are the dependent variables. T is the independent variable. Notice that's the same independent variable for each of these equations. Okay, and at t naught, the initial condition on t, I have n initial conditions. Okay, so again, I can write this system of equations in matrix form, just like I had done previously. So now I have a initial value problem in matrix form, right? So here's my initial values, which correspond to this x naught matrix, this initial value matrix, initial value vector rather. Okay, and it turns out that we can actually apply any of the numerical methods for the single equation case. We can apply those numerical methods to the vector case or the system case. So the Euler's method, the improved Euler's method, and of course RK4, the fourth order Runge-Kutta method. Okay, so let's have a look how do we do this now. Well, let's look at Euler's method. So, well, our independent variable here is t. So if you recall from the previous week's videos, my independent variable I had been using was x, but here I have t. So I start at tn plus 1 equals tn plus h. And of course I'll have a t0 as an initial condition. Okay, and Euler's method says the update to my vector of solutions x, xn plus 1 equals xn, so at the previous t step, plus h, that's the size of the step in the t direction, times f, which again is the right-hand side of this, the ODE. Again, remembering that this is a vector. So f evaluated at tn, the previous time step, or previous t step, xn, so x at the previous step. So remember, these are all vector terms, okay? And this is actually quite simple to apply to a system. Okay, so it's exactly the same formula, we just have to apply it to the system, so more than one equation at once. Okay, but it's effectively the same thing. RK4 is very similar as well, except, well, now we have something that is all made up of vector terms as well. So what I should say is that when we have one ODE, that we're solving, first order ODE, we have one independent variable and one dependent variable. Now, when we have a system of equations, we're going to have one independent variable and n, well, let's say as many first order equations as are in your system, that is how many dependent variables you have. So if I have two first order ODEs, that's system, and I'm trying to solve the system of two first order ODEs, then I have two dependent variables. So in this vector xn here, xn, that is actually made up of two variables, okay? The k terms here, which are the predictor steps, these are now, of course, vector terms. Okay, so let's look at an example here, just a very simple example. So x prime equals f. Okay, and now notice that f is a function of t, the independent variable, and x and y, which are the two dependent variables. So x prime equals this function f with some appropriate initial condition. Y prime equals this function g, which again is a function of the three variables with some appropriate initial condition. So I can write down my update formula for each of these individually. xn plus 1 equals xn, the value of x at the previous time step, plus h over 6. So this is just a feature of RK4. H over 6, see the coefficient in front of m1 is 1. So we get 1, 2, 2, 1. That's just a feature of RK4. Okay, so we have h over 6 times m1 plus 2m2 plus 2m3 plus m4. And a similar equation for y, the update for y. So m1 and k1 here are going to be our predictor steps for x and y. So explicitly writing these out, m1 is the value of the right-hand side of the ODE, x prime equals f, evaluated at tn, xn, and yn, the previous step. M2, so M2 is the function, the right-hand side of the ODE, the function f, evaluated at tn plus a half h. So this is this half step in the independent variable, which is exactly the same as in the single case, the single ODE case. But now we have two dependent variables to update, right? So we don't, previously we would have just had this part here, xn plus a half h times m1, which m1 is the previous predictor step. But because we have two equations, so two dependent variables, we also have to update the other dependent variable. So the other dependent variable is yn plus a half h times k1, where k1 is going to be associated with the right-hand side of the ODE. And in fact, let's just point out that this function, the m's here, which are associated with the update for x, are the right-hand side of the ODE for x. Okay, the k terms are exactly the same. In fact, all the arguments in here are exactly the same, except the function is g here. Okay, so the function for the k's are the predictor step for the update of y, and they refer to evaluating the function g in this ODE for y. Okay, so you can see here that these are coupled because if we want to write down m2, we need to know the value of m1, which is from the previous step, but we also now need to know the value of k1, which is over on this side here, the function g, the right-hand side of the second ODE. And similarly, if I want to find k2, I need to know both k1 and m1. So we have to solve these things all simultaneously. If you recall, just as a way of reminder, the fourth order Runge-Kutta method for a single ODE is shown here. So here we only have one dependent variable. So we have the y here, which was the dependent variable. Whereas in this vector case, in the case of two ODEs, we have two dependent variables. So we're updating, we have two sets of predictors, M1, M2, M3, M4, which should be M4 down here, K1, K2, K3, and K4. Okay, well, the theory is very good, but perhaps we should solve this, solve an example. So I want to solve this initial value problem using RK4. So I have a second order linear ODE here with some initial condition y0, when x equals 0, y equals 1. When x equals 0, the derivative of y equals 2. So x is the dependent variable here. So what I'm going to do is, well, I've already used x, so I want to use a different variable. I'm going to introduce a new variable u. And I'm going to say u is equal to the derivative of y. And if I take the derivative of u prime, this is what I get. Okay, I can write this u prime like so, with the following initial conditions. Well, when x equals 0, y equals 1. When x equals 0, u, which is just y prime, equals 2. So I can apply the update formula to our two variables now, y and u. And so I need to evaluate these m's and these k's, right? So if the function f is the right-hand side of the y prime, the function g is the right-hand side of u prime, and here are our update formulas, or our predictor steps in RK4. Okay. Well, the first step is going to be m1 is equal to u evaluated at step m, because remember, m is associated with this first equation here. So y prime equals u. So the function f evaluated at xn, yn, un is just going to be u evaluated at n. So un. K1 though, so K1 is associated with this function g. So this is going to be negative 2 times yn minus 2 times un plus e to the xn. Okay, so it gets quite messy quite quickly. In fact, I actually think it's easier to code than it is to write down these steps manually. Well, we'll come to that. I can then write down the update for M2. So if you recall, the formula for M2 was we're evaluating this function f at x n plus a half h, y n plus a half h times k1, un yn plus a half h times m1, un plus a half times k1. So that's why we have un plus a half times k1 here. And again, things get more complicated for the K2 and K3 and K4. So I think really writing this down manually is useful, and it's an exercise that you can go through. But I think really the way to compute these values is going to be using MATLAB or Octave. So I'm going to switch over to Octave Online and just work through an example. In fact, this example, solving using RK4. Okay, so here I am on Octave Online, and I've just written out our problem that we're working on here in the Octave script. Okay, so we want to use the RK4 method to find the solution to the system dy by dx. So remember, x is the independent variable, y and u are the dependent variables. So dy by dx equals u, our dependent variable, and so this right-hand side, u, is the function which we're calling f. Okay, so f is the function, basically the right-hand side of the differential equation for y. We also have the initial condition here, y0 equals 1. When x equals 0, y equals 1. Okay, and then we have the second differential equation, du by dx equals this function g, and the function g is negative 2 times y minus 2 times u plus the exponential of x. Okay. And again, we have this initial condition on u. When x equals 0, u equals 2. Okay, and we want to find this solution of y, the values of y and of u, when x equals 1. Okay. So I just also have written out the RK4 method here. So we update the x value, the independent value as previously at the previous time step, plus n, well actually this should be x0, shouldn't it? x0 plus n times h. Okay. The predictor steps for the first equation, so for dy by dx equals the function f, are given here. Okay, we're sort of evaluating this function f at xn, yn, and un for m1. Then for m2, xn plus a half h, yn plus a half h times m1, m1's here, un plus a half h times k1, so k1 is down here. Okay, these should be g's, so let's just change the function to g here. G's, fantastic. So we have the so again the updated the predictors here, k1, k2, k3, and k4. These are associated with the second ODE with the function g. Okay, and then we have the standard update equations for RK4. So what I've done here is I've chosen a step size. Just, well, you can change this if you like. I've written down my initial conditions. I've created a vector x which starts from the initial condition, so x equals 0, moves in step size h up until the final value of x, which we said was x equals 1. And I've created this solution vector y and u with the initial conditions in the first entry here. Okay, so the first thing I want to do is create a function handle for each of my functions so that I don't have to copy and paste them every single time. I can just write them out. Okay, otherwise it gets just a little bit messy, right? So what I'm going to do is I'm going to write if calc equals at. So I have to give. Okay, well, for the function f, what do I need? In fact, all I have to give for the function f is the value of u. Okay, so u, f, even though it's a function of 3 variables, in practice is actually only a function of 1 because u here. Okay, so I have to give it u, the value of u, and in fact, the equation is just function f is just equal to u. The gcalc though, well, here I have to give it three variables, x, y, and u, okay? Because the equation for g is negative 2y minus 2u plus the exponential of x. So let's just write that in here. Negative 2 times y minus 2 times u plus the exponential of x. Okay, so I don't need that to be outputted. Okay, so now whenever I call fcalc and gcalc, it will automatically calculate the values of those functions for me. Okay, so now I'm going to, I've got this loop here, which I'm going to loop through to solve each step of the RK4 method. Every time I run through this loop, I want to clear the variables m1, m2, m3, and m4. I also want to clear the variables, what are they called? K1, K2, K3, K4. Just so that I don't accidentally carry over something from the previous step. I want to make sure it's all clear. Okay, so now I need to calculate these things, right? So M1 and K1, well, we can calculate these without anything else. All we need is, well, let's just write it out. M1 is equal to fcalc evaluated at u at the point at the previous step. So u at the point I minus 1. Similarly, K1 is equal to gcalc. Okay, so gcalc takes three inputs, x, y, and z in that order. So we take the value of x at the previous step, I minus 1. We take the value of y at I minus 1. And we take the value of u at I minus 1. Okay, so M1 and K1 are quite straightforward, in fact. M2, though, well, again, we're going to use fcalc, but we have to evaluate the vector u at, the variable u at the previous step, un, plus 1/2 times the space step h, so the x step h, times K1. Okay, so that's from the previous step. So, well, let's do that. I can calculate u at I minus 1 plus 0.5 times h, the space step, times K1. Okay. K2, similarly, equals gcalc. And again, this one is a little bit more awkward because I have three inputs. I've got x, y, and u. So x is evaluated at x in, or the previous x value, plus 0.5 times h. We get x at I minus 1 plus 0.5 times h. Okay, great. Y is evaluated at y at the previous step, plus 0.5 times h times m1. So we get y at the previous step, I minus 1, plus 0.5 times h times m1. It was m1, wasn't it? Yes, m1. And then finally we evaluate u at the previous step, plus 0.5 times h times k1. Okay, and if I have not made a mistake, that should work. We need to do the same thing for M3 and K3. So actually the formula is the same, it's just we change all the K's to K2 and the M1s to M2s. And then finally M4 is fcalc. So fcalc K4, M4 is un plus h times K3. So u I minus 1 plus h times K3. And similarly, K4 equals gcalc at evaluated at the x value. So x was xn plus h. So x at the previous time step, or previous step, plus h. Y at the previous step plus, let's see, plus h times m3. So plus h times m3. Yes, that's correct, isn't it? Yes. And then u plus h times k3. Y at I minus 1 plus h times k3. Good. So I don't think I've made any mistakes there. I think that looks good. Well, let's find out. And so then we have to actually update the values of y and the values of u. Okay, well, what was that? That was y was this formula here. Y, so y at the previous step. So y I minus 1 plus h over 6 times m1 plus 2 times m2 plus 2 times m3 plus m4. And then similarly for u, I shouldn't have copied that bit. So we get u at the previous step. Okay, great. And that one has the k values in there. Yeah. So if I've made no mistakes, this should run. It's not often I do things first time, so we'll see. We'll see if it works. I may have to add more time here. It's doing a lot more steps, but no, it actually is pretty happy. Okay, so if we look at this here, the order we've outputted this is x, which was the independent variable, y, and u. Okay, so when x equals 1, our RK4 says that y equals this 1.4574 number here. And it also says that u is equal to negative 0.3375. 0.3375. So I didn't want to save that. So we have a prediction for the value of y at x equals 1. We do have to check this prediction, however. So what I'm going to do is I'm just going to check this using Wolfram just to see how close I've got. So the original ODE was a second order ODE, which we, if you recall, we turned that into a system. So let's just see if Wolfram will tell us what the solution to y is. Y prime 0. We could also calculate the exact solution for this case, right? But okay, well, this is quicker. So this is my initial value problem here, which has this solution here, okay? So I'm going to open that in a new window, and I'm going to calculate that at x equals 1, which is what we were looking for. And okay, well, this is the value at x equals 1. I would quite like that as a number, please. Okay, so 5.0056. So we seem to be miles off here. So let's go have a look and see if we can find out what is wrong. Okay, so I just found two errors here. The first one is with my actual derivation. So when I set u equal y prime as my u as my new variable, and then I took the derivative of u prime equals y double prime. Okay, so then if I come back to my original ODE over here, y double prime should have been equal to e to the x plus 2 times y prime, so 2 times u, minus 2 times y. So the sign on this 2 times u here is wrong. The sign should be plus here. So that's one problem. So let's go to Octave Online again. Let's fix that. So here we should have plus 2u instead, which means in our G calculation here, we should have a plus here. The second error I found was in my calculation for K4. See here I'm calculating the updated X value, the updated Y value, and the updated U value, but I wrote Y here instead. So this should be capital U. So the moral of the story is everybody makes mistakes when they're coding, especially when they're being recorded. So let's run that again with the same step size. And let's just see if we get a closer value to the exact solution. When I know we do because I tested it. Okay, so actually now when x equals 1, the value of y is 5.0056 and the value of u is 6.4743. The exact value of y at x equals 1 is y equals, so from, well, it's a lot of decimal points here, so let's just use 5.0056. 5.0056. Well, maybe we should use some more. In fact, the RK4 in this case is calculating our solution correctly to at least 4 decimal places here. So this is pretty good. So I apologize for the small errors that I made here, but I didn't want to edit them out because I feel like this is actually how things work in the real life. We do something which is almost right. We make a mistake, and then we come back and find the mistakes, which can sometimes take a lot of time, and we fix the mistakes. Okay. So we're going to move on now to another mistake I made. When I defined these m and k values here, I had xn plus a half h, un plus a half k3. The half should not have been there. It should be 1. Okay. So what we've done here is we have worked through an example of how to solve a system, very simple system, just a 2 by 2 system of first order linear ODEs using Octave or MATLAB. So I believe you have to do a similar thing in your assignment. You have to do some by hand and some using MATLAB. Okay, we're going to move on now to just kind of a nice happy example of numerical methods for differential equations, systems of differential equations. And so we're going to work on this example of the SIR model for disease dynamics. So what does all that mean? Well, let's have a look. So the figures here and the equations here are from Wikipedia, compartmental models in epidemiology. I just did that because it saved me a lot of time, and they're open source. And so the idea is we have this thing called SIR model, a very simple model for disease dynamics. So for example, the common cold or chickenpox or something can be modeled with what's called a compartmental model. And so this particular compartmental model, the SIR model, where S stands for susceptible, I for infectious, and R for recovered. So in this very simple model, we have a population, let's just say, of people who are susceptible to a disease such as the chickenpox. At some stage, these susceptible people who do not have chickenpox may become infected by somebody, and therefore they move into this compartment called infectious. Okay, so they are infectious for a little while, they take their medicine, they rest up, they drink some chicken soup, and eventually they become recovered. Okay, so in this particular model, we're not looking at any disease that kills people. Maybe something quite benign that you just get a little bit sick and then you recover. Okay, and so the rate at which people move from the susceptible to being infected is beta times S times I. Okay, beta is some constant. So this is some, it could be the some rate at which susceptible and infected people come in contact, so or at least the product of this is. So beta is just some constant. S is the number of susceptible people, and I is the number of infectious people. So you can see here that the more infectious people there are, the faster or the more rapidly people will move from being susceptible to infected. And then similarly, the recovery rate, so the rate at which infectious people move into the recovered compartment here is gamma times I, where gamma is again some recovery constant. So this could be related to how long it takes to recover from the disease. So if you get over it, if it's a 24-hour bug type thing, gamma could be quite rapid, quite large. If it's a thing that lasts for a week, then that'll be a different constant basically. Okay, so this is this constant times the number of people that are infected. Okay, and so we can derive equations for each of these compartments. So the number of susceptible people over time, ds by dt, is equal to negative beta times I times s over n, where n is the sum of the total population. So okay, so it's basically n is s plus I plus r. We're saying that everybody has to fall into one of those three categories, okay, in this simple model. Okay, well, the number is negative because people are leaving the susceptible compartment and moving into the infectious, okay? Similarly, the rate at which people become infected over time, so di by dt, is equal to positive beta times I times s over n. So in fact, this is the positive of this number here, because they're moving from the susceptible into the infected case, so negative here, positive here, and then minus the rate at which they move from the infected compartment to the recovered, okay? And then the rate that people recover over time, dr by dt, the number of recovered people over time is equal to gamma times I. Okay, so yeah, S is the stock of susceptible population, I is the number of infected, R is the number of recovered population. Okay, N is the sum of those three. So in this model, we're assuming that the population is constant, there are no births or deaths, and there are a few other assumptions as well. But I just wanted to throw this in there because I just wanted to say that a lot of these mathematical models of epidemiology that are going around are basically more complicated SIR models. So but they all start from the same place, this SIR idea, and then over the years this idea has been developed. And so solving these systems of first order ODEs is extremely practical in the real world. For example, in disease dynamics. And usually these dynamics are complicated enough that, well, for practical purposes, we would mostly solve these numerically. Okay. This is a nice, perhaps appropriate example of numerical methods applied to systems of differential equations. Okay, thank you very much. I'll see you in the next class.